Here is a record player or a turntable problem. It's very similar to problems of a car going around in a circle on a road. And the reason for that we'll see here in just a moment. So free body diagram says, consider a coin of mass m placed on a rotating surface, a distance capital R from the axis of rotation. The surface rotates with period t. There are some locations on the surface where the coin can be placed and the force of static friction will not allow the coin to slip. At other locations, the coin will slip because static friction is not strong enough to prevent the coin from slipping. The coefficient of static friction between the coin and the surface is mu. So let's start with our free body diagram. We're going to have gravity straight down. By the way, this is a heads-on view. We're looking at it right there. I drew gravity down 1, 2, 3 bars down there, and we will have a normal force back up, 1, 2, 3 bars back up, and the normal force must be equal to the force of gravity there, because in the y direction, everything is canceling out. So something must be pointing towards the center of the circle, and that value there has to be the force of friction. It is trying to slide out, and the friction is holding it in. More than likely, friction is less than normal force, but we don't know that for sure. That's because the friction force is almost always a percentage of the normal force there, but it's not a big deal. You could draw it larger than that. So the next thing that I want you to do is to describe this derivation that they did the work for you here. So if we look at this, I'm just going to sort of write the steps that would go here. So they say the force of friction is equal to mu times the normal force. That is just straight off the equation sheet, so you can say that that's where you got it from. Then they say the force of friction is mu mg. So how are they getting from here to here? Well, in the y direction, as we just stated on our free body diagram, the normal force is equal to the force of gravity because it's not moving in the y direction, and therefore that is mg. And so that's how you can substitute normal force with mg there. Then they sort of do a double skip here, I would think, from here to here. What you need to say is well, as indicated on our free body diagram, the centripetal force is the force of friction. And therefore, we can replace the force of friction with mv squared over r. Jumping down from here to here, you can see here that the masses will cancel out, and that's what allows us to jump from there to there. Then, on this step here, we simply multiplied r up to the other side there. So now we have v squared equals mu gr. And then here we simply took the square root of each side. So now we have v is less than or equal to the square root of mu gr. And then we get down here. They've been taking all these simple little steps like multiplying up r, taking the square root one at a time, and then they get down here and they inexplicably do a bunch of steps at once. Let me write up here what they are doing. The first thing is this v is for velocity. So velocity is distance over time, or in the case of a circle is the circumference over the period. The circumference is 2 pi r over the period there. Since that is what we're going to do with velocity. One thing they do here is they square each side. So they take this equation, they square the velocity, and they square this side, which simply gets rid of the radical there. And then we have to substitute in v squared. So we got to take all of this and square it to plug it in for there. So the 2 becomes a 4, the pi becomes a pi squared, the r becomes an r squared, the t becomes a t squared, and that is less than or equal to mu gr. And the very last step is that r there cancels with one of those r's up there, and that is where we reach this equation right here. And that equation is going to become important when we get to the arguments. So Blake and Carlos here are trying to predict when the coin will slip if it's too close or too far from the axis, and they're going to discuss different aspects here. Blake says, I think the coin will slip if it's too close to the axis. It's like a car that makes a turn too tightly. The car can slide out of control. There's not enough force if the radius is too small. And Blake's right. That is a thing that happens, but we'll get to why it's not quite right to apply it to the coin. Carlos says, I think the coin will slip if it's too far from the axis. It's like a merry-go-round. If I ride a merry-go-round near the center, then I don't feel much more force pulling me to the outside. But if I ride near the outside, there's more force pulling me away from the axis. There's not force. You would call that force a centrifugal force, but it's just that he notices inertia more. So what's going on? Let's get back to our equation here to talk about who is ultimately right. So let me write this equation bigger so we can see it. 4 pi squared r over period squared is less than or equal to mu g. This is fixed. This number would be determined by the material of the coin and the record player tabletop, and this is being here on Earth. So you can't get any bigger than that. If the radius is small, then this whole side is small, and we'll stay underneath that number and we'll be okay. That's the simplest way to look at it. If that radius gets too big, then this side is going to get too big. And remember, ultimately, this side is fixed, so we can make this side bigger than that side, and that's when it will slip. So what is Blake thinking of when he's talking about the car going around the circle? The thing that you have to remember here is that the car going around the circle, we're assuming the car is a fixed speed. And then it's true, it's harder for the car to go a fixed speed around a tighter radius. But can you see here that that circle right there is a smaller circle that will be covered in the same amount of time as this bigger circle out here. So the point is this: as you move the coin in and out along the radius here, its speed changes because it will always go around, 48 times or 45 times per minute, for example. So they all have the same distance they travel, but these guys go a smaller distance they all take the same amount of time to go around once, but this guy will go a smaller distance in that time. So it's going not as fast. And so when we get down to it here, state whether it will slip if it's too close or too far. It will slip if it's too far out there. Angela and Dominique are arguing over the mass. Well, we saw in the equation there, the mass just cancels out. But yet, at the same time, Angela says she believes a lighter coin is less likely to slip because it requires less force to go in a circle. That's true. And Dominique believes a heavier coin is less likely to slip because a heavier coin can have a greater amount of friction. That's also true. It's just when you combine the two together, then the mass winds up canceling itself out there. I'll leave you with this. Which coin is more likely to slip? Let's say that this coin right here was at halfway out, so the radius over 2. And then we stick another coin out here, and this one is 2m. This one, let's say, is m right here, and this one is 2m, and it's the full radius of the record player out there. So basically we have mass m at half the distance, or mass 2m at the full distance. Which one, if any one, is more likely to slip?